6.4, making asynchronous tasks interoperate. We're going to take a look at the async.io versions of the synchronization primitives we've seen previously, as well as at the other end of the process of async.io's versions as completed and related functions. And we're going to take a look at async.io's version of a queue. All of these things are functionally very similar to the things we've seen previously, but are designed to operate in the context of async.io's multitask, single-thread processes, rather than in the multiprocessing context we've seen previously. The async.io package provides lock, semaphore, event, and condition classes that are pretty similar to the ones we looked at in the context of multiprocess programming. They provide the same method names and fill the same roles. The important difference is that for async.io's versions, some of the methods are coroutines, and some are not. Specifically, in each case, the acquire and wait methods, if they exist, are coroutines that must be called from yield from. This is because they need to be able to pause until some specific thing happens, and only a coroutine can pause and hand off control to the scheduler. Having mentioned lock and the rest, I want to point out that while they are sometimes necessary, they are less often needed under async.io than they would be under concurrent futures or other systems which provide multiple streams of execution. That's because async.io scheduling is cooperative. It's only possible to switch between execution streams at yields, which means that if there are no yields within a critical section of code, it can't be interrupted. No other task can modify the same data at the same time, because no other task has the opportunity to run any code during that time. Thus, lock and such are only needed when a critical section of code does in fact use yield at least once. We've seen as completed and wait functions before, in concurrent.futures. Async.io's versions are coroutines, of course, but they're not that much different in how we use them. The wait coroutine still waits for a group of futures to end, with an optional timeout, and returns a list of futures that are ready and a list of futures that are not. The asCompleted function still takes a list of futures and produces in the order that the results become available. Then we extract the actual values from the futures with a yield from, and are good to go. In this code, there's no telling what order the results will become available, but each time a value does become available, it will be printed. Async.io provides some other interesting coroutines for collecting data from futures, particularly wait for and gather. The wait for coroutine lets us wait for another coroutine to finish, but with a timeout. The first coroutine on the screen right now calls another coroutine and collects its result. No timeout, no anything special. The coroutine is basically just a wrapper. The second one does the same thing, but if the called coroutine doesn't finish within 5 seconds, a timeout error is raised. The third one does exactly the same thing again, except it handles the timeout error and follows a different code execution path after that. Then there's the gather coroutine. What it does is take a bunch of futures and make a single future that will be done when all of the subfutures are done, and result in a list of the subfutures results. This is rather similar to wait, except instead of being a coroutine itself, it produces a future which produces as its result the same thing that would have resulted from the wait call. There are a bunch of uses for something like that, but one very nice thing we can do with it is to use it to construct the future that we pass into run until complete. In effect, we're telling async.io that it should run until all of these futures are complete. Futures are great for communicating one-off values between tasks, and event objects are good for sending simple signals, but sometimes we want a more fully featured communication channel. Fortunately, async.io provides us with a queue class and a few variants based on it. Async.io's queue has both the put and get methods as coroutines, and we have to already be in a coroutine to call them, unless we were actually going to use the async function to launch them as separate tasks, which would be wasteful and pointless. However, the queue class also has methods called put no wait and get no wait that are not coroutines and can be called from anywhere. In our earlier discussion of futures, we noted that using a queue would simplify the job of making a class that needed to use both coroutines and iteration. That's thanks to these methods. The iterator can use put no wait or get no wait, while the worker coroutine can use put and get, and the code comes out both cleaner and more efficient. Async.io provides a couple of variant queue types that return their stored values in different orders. Instances of priority queue give back the smallest object they contain, according to the less than comparison operator, when we call get or get no wait. So if a priority queue contains 34, 2, 5, and 97, calling its get coroutine return 2, the next time you called it would return 5, then 34, then 97. A LIFO queue, on the other hand, always gives back the most recently added object. It is, in other words, a stacked data structure. Async.io also provides a joinable queue class, which adds an extra join coroutine and a method called taskDone. With a little bit of extra work, Using a joinable queue allows coroutines to pause and wait until the queue has been emptied by other tasks. So we have all of the synchronization primitives that we'd seen previously in other contexts, but since async.io's scheduling is not able to interrupt processes and has to wait for them to allow the scheduler to switch tasks, they are less necessary in some contexts. We've also seen that it's possible to make any task have a timeout, so it runs for a certain amount of time and it either finishes before that time or raises an exception by using the wait for function. And we've seen how to combine multiple features into a single feature. That's it for inter-task cooperation. In the next video, we're going to take a look at the feature which most often motivates people to use async.io, network communication.